Good morning everyone and welcome to today's worked exam answer video. Today I'm having a look at a shapes of molecules question which is covered in the structure and bonding topic taught in the AS part of the A-level specification. Shapes of molecules is something that comes up across, to my knowledge, the AQA and the OCR specifications. So whilst this is an AQA question, what we're going to talk about can be applied to the questions that you might see in OCR papers as well. Now, it is a slightly older AQA question again. We've got 8 marks here. This would not be an 8-mark question in sort of today's papers, but all of the content that we're going to put down in our answer for this question is still relevant to what we would need to give today. So yeah, probably feels a bit harsh to know that we're going to get fewer marks for this in today's sort of exam papers than we would have done kind of before the spec change, but it is what it is. We need to understand the content. That's what we're going to focus on. So it says, explain how the concept of bonding and non-bonding electron pairs can be used to predict the shape of and bond angles in a molecule of sulfur tetrafluoride SF4. Illustrate your answer with a diagram of the structure. So when they say bonding and non-bonding electron pairs, the non-bonding is probably what we would know today as the lone pairs more generally. Certainly that's what I know them as. So we work out how many bonding pairs there are between the sulfur and the various fluorines in this case, and then we'd be looking to see whether sulfur had any electrons that were not being used in those bonds, hence non-bonding, that we would then count up as our lone pairs to deduce the shape. So we've got to give shape and we've got to give the bond angles, and that's our molecule that we're dealing with, and then we've got to draw a diagram. Okay, so the first thing that I'm going to do is look up sulfur on the periodic table, find out what group it's in, because if I know what group sulfur is in, then I know how many electrons it has available to use in bonds with, in this case, the fluorines. So sulfur is in group 6, and therefore we've got 6 electrons. Again, we're thinking a bit simplistically here in terms of the 6 outer electrons like we did at GCSE, but it works perfectly for every A-level example, so we're going to go back to that. We're thinking about sulfur because sulfur is going to be our central atom, and the fluorines are then going to be surrounding the sulfur in the middle. Then what I would do is I would have a look at how many bonds the sulfur is forming with however many fluorines we've got. So we have got sulfur to fluorine bonds that are going to be formed, and we're going to have that 4 times because we've got tetrafluoride, so 4 lots of sulfur to fluorine bonds. Now, in each of those covalent bonds, the fluorine will share 1 electron and the sulfur will share 1 electron to give us sort of a shared pair that has been contributed to equally by each of our atoms. So if sulfur is going to give up, or share rather, 1 with each fluorine, then that's going to use up 4 of its 6 electrons. And what that enables us to do is see that we're going to have 2 electrons left over that sulfur will not be using in bonds. So to use their language, we will have bonding pairs. We're going to have 4 bonding pairs between the sulfur and the fluorines, and then we've got 1 non-bonding electron pair or 1 lone pair on the sulfur. So I would then go for 4 bonding pairs, 1 lone pair, and just remember, because we are thinking about pairs, this number here will either have to be none for no lone pairs, 2 for 1 lone pair, 4 for 2 lone pairs, 6 for 3 lone pairs. Okay. Now, this isn't a combination that we need to know for AQA or OCR. And it wasn't a shape that we needed to know in the past either. This is then an application question whereby we're having to think, okay, we might not know exactly what this shape is going to look like, but using our knowledge of the shapes that we do have, when we have 5 electron pairs and their 5 bonding pairs, it would have a trigonal bipyramidal shape. So our shape that we draw, we don't have to name it, we just have to draw it, is going to be based on a trigonal bipyramidal structure. And what we're going to need to do is think about where we're going to put our lone pair. And that will come from thinking about electron repulsion theory, which we'll come back to in a second. So if we then have our sulfur at the middle, we need to, for a trigonal bipyramidal shape, be comfortable drawing it, know where all the bonding pairs would be positioned. So we've got our 2 axial positions, so top and bottom, and then we've got 3 equatorial positions, so around the middle, where we've got one that would then be coming out of the paper towards us and one going back into the paper behind us. So that would be our trigonal bipyramidal shape, assuming we had 5 bonding pairs. We don't have 5 bonding pairs, we only have 4. We then need to think about the best place to put the lone pair. Now, if we had multiple lone pairs, we would need to remember that lone pair to lone pair repulsion is the strongest type of repulsion we can have. So electron pair repulsion theory states that repulsion between lone pairs is greater than the repulsion between a lone pair and a bonding pair of electrons, and that is greater than the repulsion between 2 bonding pairs. So lone pairs want to be as far apart from other things as possible, which is a bit tricky really given the shape that we have. If I was to put top or bottom, they would accept that quite happily. So let's say I put a lone pair down here, the lone pair would then be 90 degrees away from these bonds. Not quite 90, but I'll come back to that. Whereas if I was to put put my lone pair in one of these middle positions, it would then be 90 from this and this, but it would actually be 120 away from the 2 around the middle, which I think is slightly better, but either is okay on the mark scheme, so long as we can then think about the position of the lone pair and what that's going to do to our bond angles. So I'm going to put my lone pair there, which is my 2 electrons and then my little lobe of my orbital, but they look like little aliens when I draw them like that. And then I'm going to put my 4 bonding pairs there. Now we don't need to know the name of this, but pretty sure it would be a seesaw, because if I rotate this way, we've got the base of the seesaw and then the parts where you would sit. Anyway, that is not relevant at all. You do not need to know the name of that shape, so please do not worry about that. So explain how the concept of bonding and non-bonding electron pairs can be used to predict the shape of and bond angles in. So we've based it on a trigonal bipyramidal shape because that is when we've got 5 bonding pairs. And then we need to now think about the electron pair repulsion theory. So the first thing I'm going to do is just specify the order of repulsion as I just said to you guys. So electron pair repulsion theory. So lone pair to lone pair repulsion is greater than lone pair to bonding pair repulsion, which is greater than bonding pair to bonding pair repulsion. So that means that my lone pair is going to push the fluorines around the equatorial positions away from itself, and they're going to end up getting closer together than they normally would be. So normally the bond angle between the equatorial positions will be 120, but it's actually going to get squidged, compressed a little bit by the lone pair repelling the bonding pairs away from itself. And because the lone pair bonding pair repulsion is stronger than bonding pair to bonding pair repulsion, the bonding pairs just have to suck it up and get closer together. It's also going to push away these ones as well. So thinking about how that's going to work, pushing it kind of that way away from itself, then again you're going to have different bond angles then between the axial positions and the equatorial positions as well. So they would normally be 90, but if you've got a bonding pair repelling those axial positions, and again squidging, we're going to have less than 90. And that's the key thing. We don't need to be able to specify how much smaller than 120 or how much smaller than 90. We can just say that they will be smaller than 90, smaller than 120 because, and then explain our answer. So bond angles will be less than 90 degrees and less than 120 degrees. I'll put in brackets, which are the bond angles in a trigonal by pyramidal shape, because the lone pair of electrons will repel the bonding pairs away from itself, and because lone pair to bonding pair repulsion is stronger than bonding pair repulsion, the bonding pairs of electrons will end up closer together. I think that covers everything I need. So explain how the concept of bonding and non-bonding electron pairs can be used to predict the shape of and bond angles in a molecule of sulfur tetrafluoride. Illustrate your answer with a diagram of the structure. I've got my diagram. I've got how we worked out the number of bonding pairs and lone pairs, what shape we're basing our molecule on, electron pair repulsion theory, and then we've thought about how the lone pair will affect the bond angles between the bonding pairs. Fab. That can be applied to any of the examples that you do need to be familiar with, but equally any of these sort of application examples as well. So if anything I've said about kind of getting the number of bonding pairs and lone pairs or electron pair repulsion theory doesn't make sense, and you want any clarification, as always, please just let me know. Thank you so much for watching, guys. I hope that you have a really good day, that everything's good with you, and I'll see you soon. Bye.